Okay, let's start. So today we will talk about truth table and the CMOS. So here is one example of two input AND gate. We have input A and input B. So totally we have 2, 2, 2, 4 rows in the truth table. And you can list all the possibilities combination of A and B, and then write the output in the truth table. And here is one example of a 3 inputs AND gate. So the input is A, B, and C. The output is F. Then we have a 2, 2, 3, which is 8 rows in the truth table. So basically, you can see that the truth table is equivalent to this gate. The truth table can describe the function of this logic gate. So when you have the value of A, B, C, by looking at this table, you can have the output, whether it's a 0 or 1. But the real logic gate here is actually compute this Boolean equation. So when we write the hardware language, we just describe the function, Boolean function of a piece of circuit. And then eventually the EDA, the Vivado, the EDA software or algorithm will actually implement your logic function, your Boolean function, by some logic gates. So you can write your HDL language here. And then you can input process technology like 45 nanometer. You prefer to use 45 nanometer or 32 nanometer or even 4 nanometer process technology. And then the software can synthesis, do the synthesis, build your logic by some basic gates like the universal NAND gate, which we introduced in the previous lecture. And of course, it will apply some simplification optimization algorithm to reduce the hardware overhead of your circuit. But again, it should be able to maintain the same Boolean function. Then eventually you can have a piece of circuit like this here. So this is one gate, and you also have all the connections here. And then you can do another level of simulation. So in your homework 1, we just do some logic level simulation. By logic level simulation, you can have the function like this truth table. You tend the input here, and then you have the corresponding output. It's very straightforward. But after the synthesis, after you actually consider those gates, you will have some extra information. For example, how fast your circuit can run. If you use some old process technology like 45 nanometer process technology, maybe your circuit can only run at 1 gigahertz. If you have some advanced gates or process technology, your circuit, for example, 4 nanometer, maybe your circuit can run at 1.5 gigahertz. So when you actually consider the technology here, you can simulate more. You can simulate more information in your simulation. When you set the circuit to run at 1.5 gigahertz, your simulation result will not have any error. But if you further improve the frequency to maybe 3 gigahertz, then you may have a lot of timing errors. So again, the truth table can be implemented by the gates. Another method to implement this logic is to directly use this truth table. You can do the lookup. For example, when you have the ABC value 101, you can read this one and then do the lookup to know the output value. So in this way, it's possible for you to directly store this table into some memories, into some buffers. This is so-called FPGA. It's reconfigurable. Why? Because you can change the value of your truth table. For example, you can write this 0 and 1. Then you just do the reconfiguration. And then potentially you can have a lot of inputs or values. Then potentially your truth table can be very large. So in this way, you can have multiple buffers. And these buffers can be connected by some connections. And the outcome of these connections can be also reconfigurable. So in this way, maybe you have a medium-sized truth table. You can use this buffer. And you can also use this buffer. Then you can connect these two together. Maybe the first half is stored in the first part. The second half of the truth table can be stored in this part. And then you can configure these connections to connect them together. So we can see that the truth table is equivalent to the Boolean algebra, to the Boolean expression. So how to convert the truth table to the Boolean equation? When I provide you a truth table like this, how can you know what's the corresponding Boolean function? Then you can use the canonical form like this one. The canonical form is the sum of the products. So each term here, each argument here is a product, and then you can sum them together. So each term is corresponding to one row, which can generate a one output. For example, for this row, this is the first row, which can generate a 1. This row is related to this one. Because A is a 0, B is a 0, C and D are 1s. So we have A bar, B bar, C and D. And then we can pick up all the 1s here. The row can generate 1. We have 1, 2, 3, 4, 5, 6, 7. We have 7 terms. And then we can sum them together. And then we can apply those laws. For example, the identity law. Eventually, we can simplify the Boolean equation into this one. So in this way, we can convert this truth table to the Boolean equation, and then we can use a circuit to implement this one. And actually, we can use a circuit to implement the first part, but again, it's more complex, and it will cost you more hardware overhead. Or I can give you this circuit and ask you what's the function of this circuit. So in order to analyze this function, you can set some intermediate variables. And then you can break this large circuit into pieces. For example, this is one piece. This is second piece. And you can write the function of this piece first, and then the second piece first. And then sum them together. So when you have this Boolean function, you can easily get their truth table here. Because we have 4 inputs, so totally we have 2 to 4, which is 16 rows. And then we can write the intermediate variables value here. And then eventually the final output, which is a z. So in this way, we can convert the Boolean function back to the truth table. So if we have a truth table, we can use the canonical form sum of product, and then do the simplification, and then get the Boolean function. If we have a Boolean function, we can set some intermediate variables, do some analysis, and then have the truth table. So they are equivalent. I mean, the Boolean equation, Boolean function, and the truth table are equivalent. So eventually, the Vivado software will help you to place and route and connect all the circuits together into one pieces. So after the you have this so-called layout. After you have this piece of design, you can do another level, post the layout level simulation. By doing this level simulation, you can consider a lot of extra information. For example, the var delay. You have a lot of connections here. Those connections have resistance and capacitance. They will introduce extra latency because of the resistance and capacitance delay. And by doing this simulation, you can consider whether your circuit, whether your design can tolerate those delay or not. And then do some modification to, help you to tolerate those delays. So here is one real example, which is an Apple CPU. So the Apple design a CPU because they need to fabricate it very fast. So they ask 2 different companies to synthesize and fabricate their chip, the same chip, which is a Samsung, and the other one is a TSMC. So you can see that different industry companies may have different process technology. Even for the same design, they will have a totally different chip design because they have different gates, different technology. And you can see that Samsung chip is smaller than the TSMC, even for the same design, for the same logic function. You can consider Apple generates a logic Boolean function. And then they use different technology to do the synthesis. They have 2 different layouts. One layout, of course, is smaller. And this smaller layout will consume less energy. So I give you this example to explain that the synthesis can actually have some impact on your mobile phone lifetime. So it has a very significant impact on your product. So even though everyone pay the same price, they may have different products. Someone need to recharge their phone more frequently. Assume that they have the same application workload. So during the fabrication, we want to make a lot of chips on this side. During this process, inevitably, we will introduce some defects, and then those chips will be broken. We cannot use them. If we can make the chip into a smaller size like this, then we have a higher yield. Higher yield means we have a larger percentage of good chips. But if the chip area is larger, then the yield is lower. So in the previous example, and of course we will prefer this design because this design has a smaller chip area. Again, you will pay, let's say, $100 for this die anyway. If you have a higher yield, which means that you have more good chips which can work properly, then the price of each chip can be reduced. Then you have a larger benefit margins, and you can make more money. However, if your chip area is large and your yield is lower, then people have to pay higher price for the same chip. Eventually, all the circuit will be synthesized into CMOS gates. And we introduce some logic view of those gates, like the AND gate, OR gate, NAND gate in previous lecture. But the real CMOS is something like this. One logical gate can be NMOS gate or PMOS gate. You can consider each gate like a switch. So for the switch, we have three input. We have two input. One is here, the other one is here, and then this is the output. For the NMOS, if I apply one here, then the switch is actually closed. Then this input can be passed through this gate and arrive here. But if I apply a 0 here, then this input cannot pass through this gate. This gate is open, and you will never a 0, no matter what the input is here. For the PMOS, if I apply a 1, this gate is open. If I apply a 0, then this gate is closed. And this signal will pass through this gate and arrive here. So typically, people use both NMOS and PMOS to implement a logic gate because PMOS is friendly to the VDD, friendly to the 1, and NMOS is friendly to the 0, to the ground. The so-called friendly means they are stronger when they pass through some signals. Like PMOS is stronger when it passes through 1s. Stronger means it can deliver a more strong signal. So here is one example. The easiest example is a NOT gate. So we have one single PMOS and one single NMOS in this NOT gate, which are two MOS here. So this is the truth table of the NOT gate. This is logic gate. So these are the knowledge you learned in previous lecture. But in this lecture, we will try to analyze the status of each MOS here. So for the case of 0, A is 0. Then the PMOS here is a 0. The PMOS here is a closed because this is a 0. But the NMOS is open. NMOS is open means that this 0, this ground cannot pass through this gate or run 1. But the VDD, the 1 can pass through this P gate and arrive at 1. Then Y is equals to 1 in this case. So you can write this table yourself. Y is 1 and A is 0. So if A is 1, then this one is open. So the 1 here cannot pass through this gate. But this one is closed. And this 0 can pass through this gate and arrive at 1. So this is a 0 here. So in this way, it's a NOT gate. Here is a more complex example, which is a NAND gate. We have 2 inputs here. And then we have 2 PMOS, which are connected in parallel. And we have 2 NMOS, which are connected in sequential. And then we will analyze each cases here. So if A and B are 0, these 2 are closed because A and B are 0. These 2 points are 0. And the P1 and the P2 are closed. Then the VDD can pass through these 2 gates or arrive at 1. When these 2 are 0, A and B are 0s, N1 and N2 are open. So the ground cannot pass through to the right. Then Y is 1. So in fact, unless A and B are both 1s, this ground, this 0 cannot pass through them or arrive 1. Why? Because they are connected sequentially. However, anyone in A and B is 0. One of these PMOS will be closed, and the VDD will pass through it and arrive at 1. So both of these 2 rows will generate a 1 here. And the last row, neither P2 and P1 can be closed, but these 2 will be closed. So the ground will pass through a 0 to the 1. And for the last row, we have a 0 here. So here is a more complex example. This example to ask you to implement this function, which is f. And then we have A, B, C, D, 4 inputs. So in order to implement this function by NMOS and PMOS, we need to implement the pull down network and pull up network separately. To implement this pull down network, we invert the output here. and then do the implementation. For example, after the inversion, this F will become F bar, and then the equation will become this. And then we know that in the pull-down network, C and D are parallel, in parallel. So we write them in parallel. And this parallel structure will be separately connected to B. And then A will be connected to the D2 in parallel in this way. For the pull-up network, we can apply the De Morgan law on this F, and then implement this piece of logic directly. So in this way, I will write down the De Morgan law first. After we have the De Morgan law, we know that C and D should be connected in sequential. And the B will be connected in parallel with C and D. And then the A will be connected to that structure in sequential, because we have an AND here. So in this way, we can have the pull-up network. And then we have the entire logic circuit like this. Again, the C, no matter it's the CMOS or PMOS, it's not perfect. It has a resistance. And the resistance is proportional to the length of the gate, and inversely proportional to the width of the gate. So when you use a different process technology, when you change the length and the width of the gate, you need to recalculate the resistance. And we also have a so-called capacitance. So this is the equation for the capacitance. Because of the resistance and the capacitance, eventually we will have the RC delay. The RC delay means that I change the input on the input. I change the input here from 0 to 1. But I cannot narrow this change on the output immediately. It has some delay. And this delay is a so-called RC delay. So in your logic, you expect that you can narrow this change immediately. But that's not true when you consider those gates. You have to, tolerate this delay in your design. So when you have a NOT gate like this, when you consider the resistance and the capacitance, you can do some analysis on that. You can draw equivalent circuit like this. You can consider the resistance here, and you can add a capacitor here to analyze the RC delay. So in this example, this NOT gate is actually equivalent to this one, because the PMOS will have a resistance and the NMOS will have a resistance. And both of them will have a capacitance. RC delay is not the only problem that you have to consider when you synthesize your circuit into by some gates. Another problem is the power. For the power, your circuit has two types of power. The first one is the static power. When your circuit is connected to the power source, you will have some leakage. You have to pay the power. This is so-called static power. So this is only related to the VDD. When you try to run your circuit, when you try to run some application on your circuit, when your circuit is busy, your circuit has to pay the dynamic power. So you can see the dynamic power is proportional to the frequency. So when you actually run your circuit, you have to pay more power. The higher frequency you run, the larger dynamic power you have to pay. So here is one example of how to compute the power consumption of a tablet. You have to consider the dynamic power and the static power separately. Any question?
In one of my other classes, I saw that there was like a NAND gate. I don't remember how many CMOS there was constructed, but that basically NAND and NOR of the piece are basically the most primitive thing.
That's right. That's right. Why? Because they are universal gates, and we have shown that the NAND gate. We can use a NAND gate to implement a NOT gate, AND gate, OR gate, all the other types of gates.
So that's there was like the PMOS and CMOS, basically like the physics of it.
Yes, yes, of course. So this is the NAND gate. So eventually, all the company will highly optimize this type of gates.
Yeah.
So all the logic will be implemented by this only one type of gate. So if you have a question, you can email me. Otherwise, we can stop today. Thank you very much.